In this video, let us deduce Kepler's first law of planetary motion, which is also called as law of elliptical orbits, using the concept of central force. Generally, the Newton's law of gravitation, Coulomb's law, Kepler's law all come under in a general force inverse square law of forces. We have a general equation which represents inverse square law force as f of r is equal to minus k by r square. Let us take it as equation number 1. For u equal to 1 by r, this f of r becomes, in place of r let us write 1 by u, then on the right hand side it becomes minus k into u square. Let us take this as equation 2. The differential equation for any of the orbits is given by, this is the general equation, d square u by d theta square plus u equal to minus m by j square u square into f of 1 by u. In equation 2 we have the value of f of 1 by u. Let us substitute this f of 1 by u equal to minus k u square in equation 3. We get on the left hand side it will be d square u by d theta square plus u. On the right hand side a minus is in equation 3 and there is also a minus there in equation 2. So it becomes plus. So m by j square u square, in place of f of 1 by u we write k u square. Here we could see u square in the denominator and the numerator, they will cancel out each other. So simplifying we get d square u by d theta square plus u equal to mk by j square. Now let us bring this mk by j square to the left hand side. When we bring it, we get d square u by d theta square plus u minus mk by j square. See, let us take this as equation number 4. In equation number 4, this second term and third term can be taken as x. So in place of u minus mk by j square, let us substitute x. And if you differentiate with x with respect to theta twice, we get d square x by d theta square is equal to d square u by d theta square. So we can rewrite equation 4 in terms of x as d square x by d theta square plus x equal to 0. Let us take it as equation number 5. We can write a simple solution for this equation 5 as x is equal to a cos into theta minus theta prime. Equation 5 is a second order differential equation which can be easily solved, and a solution can be written in this form of equation 6 as x equal to a cos theta minus theta prime. Here a and theta prime are simply the constants of integration. Again, let us substitute the value of x now in equation 6, that is in the solution part. If we substitute u in place of x, we get u minus mk by j square is equal to a into cos theta minus theta prime. So we started our derivation with assumption u is equal to 1 by r. So let us substitute u equal to 1 by r. We get 1 by r minus mk by j square is equal to a cos theta minus theta prime. In the next step, what we do? We bring this minus mk by j square to the right hand side. When we take it to the right hand side, we get 1 by r equal to mk by j square plus a cos theta minus theta prime. Next, what we are going to do is, in right hand side, we are going to pull mk by j square from both the terms. So when we pull out this mk by j square, the first term will be equal to 1 plus The second term becomes, since we do not have mk by j square, we have to multiply it by j square by mk into a cos theta minus theta prime. Then let us take this mk by j square in the right hand side to the left hand side. Then it goes and sit in the numerator in the left hand side. So it is mk by j square by r equal to 1 plus j square a by mk into cos theta minus theta prime. Again, we are going to bring in two more constants. This mk by j square is replaced by a constant L, and j square a by mk is replaced by another constant E. This constant E plays a big role driving this planetary Kepler's law of planetary motion. So replacing these constant, we get L by R equal to 1 plus E cos theta minus theta prime, which we are going to write it as equation number 7, where the constant Ls is equal to mk by j square and E is replaced by E replaces j square a by mk. So we got equation 7, L by R is equal to 1 plus E cos theta minus theta prime. This equation is the equation we have got for an orbit of a particle which is moving under inverse square law of force. As I said, the value of E, the constant value of E is identified as E equal to root of 1 minus 2 E j square by mk square with the help of two first integrals of motion. Even we have also derived one of the integrals of motion in our previous video. So the second integral of motion helps in finding out the value of E, which we are going to call it as eccentricity in the later part of this video. E is equal to root of 1 plus 2 E j square by mk square. Again, theta prime is we have already mentioned that theta prime is a constant of integration which can be easily obtained by taking the or by applying the initial conditions. So this equation comes out to be the general equation of a conic section with one focus at the origin and the eccentricity E given by root of 1 plus 2 E j square by mk square. So this equation 7 is identified as the general equation of a conic section with the focus is at 0, that is at the origin, and it has a eccentricity E. We all know what is a conic section. A conic is you can carve out 4 different shapes from the conic section depending upon the magnitude of E. The value of E decides the nature of the orbit or nature of a conic. See, if the eccentricity is greater than 1 and the total energy E is greater than 0, the conic section obtained will be a hyperbola. Generally, we can carve out 4 different conics from 4 different shapes from a conic section. One is a circle, the second one is an ellipse, third one is the parabola, and fourth one is the hyperbola. All these 4 shapes depends on the values of eccentricity. So this has been tabulated here. If E is greater than 1 and the energy is greater than 0, the conic we get is the hyperbola. If the value of the eccentricity E is equal to 1 and the total energy is equal to 0, then we obtain parabola. And if we get the eccentricity less than 1 and the total energy is less than 0, then we get ellipse. If the eccentricity is 0 and the energy is equal to minus mk square by 2j square, then we get circle. Here, to make the things very simple, here we are going to take theta prime is equal to pi, then our conic equation 7 reduces to L by R equal to 1 minus E cos theta. So, the conic section here will define what the above equation will represent depends upon the value of E. Thus, we can say the path of the particle under a inverse square law force due to the center of force in space could be bounded like an ellipse or an ellipse, or unbounded like an parabola or hyperbola, depending on the value of eccentricity and the sign of the total energy. If in case, above all, the sign of the total energy will give us the nature of the orbit. If in case the total energy is less than 0 or negative, the orbit is the ellipse. This is what actually the case of the planetary motion. So when a planet is moving around the sun and gravitational force, it takes an elliptical path. This is what we call it as Kepler's first law, the most celebrated, the basic law which helps us to understand the planetary motion. So, which is stated as every planet moves in an elliptical orbit around the sun, with sun being at one of the foci. Thus, we have derived the first law of Kepler's planetary motion using central force. The chief or the most important usage of central force problem is solving Kepler's problem. Generally, why we call it as a Kepler's problem means whatever the statement Kepler has given or he has stated, or based on his observations of the movement of the stars, motion of the planet and sun. But he do not have any theoretical presentation for his work, or for his observation. Thus, central force gives an theoretical deduction for his first law. So here we could see the different types of orbits being represented. So for the first one is in circle with eccentricity E equal to 0. Then we have an ellipse with has eccentricity less than 1, and the parabola E equal to 1, and the hyperbola, if you have eccentricity E is greater than 1.